And again, welcome to the webinar on testing cement. And I will repeat our cementing course, live cementing course this May in Lafayette, Louisiana. You can get more information at thoroughbond.com or by contacting Jill at her email address, support@thoroughbond.com. The agenda for this evening's webinar on testing cement. We're going to give you a quick pre-webinar quiz. We're going to talk about the cement lab and then the 6 basic tests that we do every day in the lab, followed by a session on some of the other important tests, and then a discussion anyway on testing cement and using the lab to save money, or how we approach testing cement to make cost-effective slurries. And that's the agenda. We're basing much of what we're talking about, or at least we're going to touch upon, the API recommended practice 10B-2, recommended practice for testing well cements. And not only do we have a 10B2, we have a B3 for deep water. We have a B4 for foam cement slurries. We have a practice for shrinkage and expansion. Within this document, we touch on Arctic cementing and a lot of things that we won't get to in this short session. Do you use API? I'll ask a couple questions to start. Do you use API practices? And I'm showing you a document here. Actually, there's a newer version reaffirmed in 2019. But do you use API in your lab or in the company that does the cementing work for you? And again, if you're a student or a young professional that has not gotten involved in the labs, the slurry that we pump into the oil well is designed or tested, confirmed in a laboratory. Cementing labs all around the world are testing these cements every day. Do you use API? Yes or no? And we're going to have a conversation. Those of you who are watching the recording of this, not live, just think along with us as we have a conversation. We're going to have an interactive session where I mainly drink coffee and ask questions. So, do you use API or any comment related to that? I also ask questions now and then. When you're in a webinar and you're just speaking to the camera or speaking to the screen, you always want to make sure people are actually on the other side. And I haven't gotten a response yet. This is where my audience needs to come in and say, yes, we use API. There we go. Thank you, Fred. You do, okay. Does anyone not use API? Do you follow API strictly would be another question. But we mostly use the recommended practices. So let me ask you some questions about that in a pre-webinar quiz. According to API, and you're allowed to say, I don't know the answer to this or leave me alone. But according to API, what should be the temperature of the mixing water when doing a lab test? Do you do the lab test, the mixing water temperature at room temperature? Do you make sure that temperature is 73 degrees plus or minus 2F? Or do you try to mimic field conditions? Okay. We get an honest, I don't know. And I've been testing, as I'll talk about later, for almost 40 years. And I didn't know the answer to this till I revisited API. So it's okay. I like the C with the question mark. What does API say, and what we do sometimes is different though, isn't it? And when we're working with API and when we're not, it's easy to get a little bit off the mark, and we're going to talk about that. The answer is, I believe, is C, same as the field conditions. However, API will say if you do not know the field conditions, then you go back to the 73 degrees plus or minus 2F. And API talks about the cement being that temperature, the mixing water being that temperature, and the equipment being that temperature. So here's another question, not really API question, but what if your mixing water is 105? What's the big deal? Will that affect your results? And let's think of thickening time, for example. Will hot water 105 instead of 73 affect your result? And if it does or doesn't, if you think it does, have you confirmed that? The answer, and yeah, okay, A and B, getting some answers. When I worked in West Texas, I worked for Oxy. We tested this with Halliburton. The concern was in the summer, having water on location that was hot, and how would it affect our slurries? Should we shut down the job? Should we continue on if we measured the temperature of our water and it was 105? And so we did a huge project, and for our conditions, our cement slurries that we pumped in West Texas, the answer was A, only for accelerated slurries. We did not see the difference except when we had calcium chloride or a densified type cement that was accelerated. However, that is something that you would have for yourself there. Sorry for the interruption. Another quiz. According to API, how many times should you puddle the cement after it is poured in a compressive strength mold? And by using the puddling rod, taking the rod and going back and forth in the slurry rigorously to let the air, the entrained air, escape. How often, or how about approximately how many times? Is it A, 10, B, 30, C, 52, or D, dependent on each lab? I should have put E. Why would API talk to you about how many times you should puddle? And so what I'm trying to say, if you read the API document, which is almost 200 pages or more, I think it's about 200 pages, you're going to find things in the document that are very specific, such as puddling. And we don't always look at all of the details of API or follow all of the details. The answer is 30. But did you know that the procedure is not to fill up the chamber here with cement, the cube mode? It is to fill it halfway, puddle 30 times, and then finish filling. And I would wonder how many labs fill up half of the cube, puddle it, and then fill up the rest. I've never done that. I've always filled it up. I would suggest it's an interesting read to go back and read through the APA document on testing, especially if that is the heart of what you do with your job. Another question with that chamber, should you have 3 cubes for each test according to API, or can you get an average with 2? Is that enough? Yeah, question is, how'd they get that number? I don't know. But I've been on API committees, and I got to be careful because I'm recording this one, but someone said, oh, we puddle about 30 times, I guess. I don't know how they got the answer, that number. And again, the answer here, it's recommended that yes, 3 cubes, although I know I've put 2 in autoclaves before and tested 2 throughout my career. And when you do that, you're getting just a little bit off API. Let me ask this question before I ask the final question, and that is, how do you then, whether you puddle 30 times or 10 times, whether you do 3 cubes or 2 cubes, whether you operate at 73F mixing water or 77F mixing water, how do you learn to test cements? And if you have a service company working for you, how they test cements? How do you learn to do the tests correctly? How do we learn how to do lab tests? I'm going to come back to that again and again. We're going to go through the tests, but I do not want to spend the next hour and a half just talking about the tests. You can read the manual for that. You can go to a lab manager and say, quickly explain to me. I really want to look more at how this impacts your operations or what's going on. Are we doing it correctly? So my question to you is, how do you learn how to do these tests, or how do you know that your lab is doing them correctly? Or how did they learn how to do the tests? What's the answer to that? And I'll revisit that as I explain more where I come from with lab testing. Much of my career has been spent in the lab testing. And again, I'm waiting for you to engage with me. How do you learn how to do the tests? A knowledge, good answer, Vahid. A knowledge of API, you know API, and the right experiences. So you kind of test it. You kind of try to prove what API is saying. How else? How do you learn? Thank you, Fred. Through training. Someone tells you, just like we're talking tonight, you're not going through API, but I'm going to say some things about API, and I may have misread. I may lead you astray a bit, but you're going to hear something. It's going to be passed on to you. Every lab I've worked at several. There we go, working as an intern. And when you go to work as an intern for a service company, every service company you go to is going to do it differently. And within the service company, every lab you go to is going to do it differently. Trust me, they will. It may be something minor, but it will be different. And so you learn the lessons, you are taught a routine of how to do testing. So my final question to you is, as you learn a routine, I ran a lab for a long time and worked in a lab for a long time. I then moved over and started running a racehorse and going through a detailed routine every day, the same thing occurring every day. And before you answer this question, which is more difficult, running a racehorse or running a cement lab, they both are built on routines. With the racehorse, I will show you we do a routine every day the same. Nothing changes. As a matter of fact, the horse loves routine. The horse loves routine more than a lab manager loves routine, and a lab manager loves routine. Before you answer, I won't go through all of these, but every morning, and this is our horse Peeboo. She's now retired and with another owner, but Peeboo was a champion racehorse, and every morning, this is one of the first things that happened. She got her food and water in the stall cleaned, and then her legs were clean, because you're putting things on the legs of horses every evening or every day, and you're washing it off every morning. So this is the first thing we do in the routine, and then everything that follows there is done every day. And you can do this routine to be successful, or you can eliminate many of the things. The job doesn't get easier. A routine built in is a routine. You get used to that work, but you start getting lazy, taking shortcuts, and you are not successful. And as time goes on, we have a tendency to take shortcuts, so you can have good lab routines and poor lab routines. But I believe running the lab is more difficult. And you see the complexities, as we'll talk about when we do our lab testing. I've had the opportunity to see that complexity quite often, both at Halliburton and then at Oxy and then at Talisman and Repsol. I had the opportunity to go to many labs, audit many labs, test at many labs. I worked for Halliburton for almost 25 years, all around the world. And then I worked for Oxy, Talisman, and Repsol as their global cementing advisor, where I would go to places like Comodoro, Argentina, and I audited for and tested 4 service companies. And of all of the tests that we did, let's talk about the 6 basic tests. Not one test was done the same way by any lab. And I still have yet to go from Comodoro to Melbourne, well, actually their lab is in a small town called Sale, Australia, or in Aberdeen, or in Calgary, or in California, and seen the same techniques used exactly followed. There are so many ways to vary in testing. And so learn what your lab does, how it operates, and then you can make adjustments, maybe slightly, but you're dealing with routine. So learn how to work with that lab and see how the results are achieved. Then you can make some good decisions on that lab test. We have 6 tests that we do all over the world every day of the week, every week of the year. And we get routines that are so strong that we better do it right, and it better be there, or we will, it will get locked in as a bad routine. We do 6 tests. We're trying to find out 6 properties. I call them performance properties of the cement. Do you know what those are? We're going to talk about cement mixing. We're going to talk about conditioning the slurry, bringing it to the right temperature, sometimes temperature and pressure. What are those 6 routine lab tests that we do every day? What are they? We do 3 just after we mix the cement. We do 3 after we condition the cement. Although for any test, you can condition the slurry, I suppose. Name those for me while I sip my coffee. I know you know them. I don't know how the recording will turn out, but I think there's a bit of, there we go. I was going to say a bit of a delay. We have viscosity. Let's call that rheology. We're finding out viscosity and yield points and gel strengths, that sort of thing. And compressive strength, that's 2. Thank you, Vahid. We have the density and the thickening time and the fluid loss and free water, along with the rheologies and the compressive strength. Thank you, Fred. Those are the 6. I'm thinking there's a delay, and Fred's saying, no, I'm just typing it all out. Good job. Those are the 6 that we do. If there is another test that you do regularly every day, and it might be a gel strength, which is kind of related to the rheologies, let me know. Is there any other test that you do every day? If you're watching by video and you do, send it to me, to my email. I would be interested to know what it is. But when you do 6 tests every day, one of my first jobs with Halliburton, I was transferred to the Oklahoma City lab, and for 6 months, I did the same tests every day for 6 months, and I learned a lot. Whether I was learning totally correctly or not is another question, but I was learning a lot because I'm seeing the process all the way through. I'll talk about at the end of the webinar, can we connect that to what's going on in the field? If we can, then it's very valuable learning that occurs in the lab. But you're doing these tests again and again and again. So you see the effects of different things that you do to the slurry. Yeah, say that, Vahid, again. Was not routine. Can you say that? Vahid is asking me a question. Was not routine question mark, and I'm not sure what that means. And while you expound on that, let's go to mix the slurry. We're mixing a slurry here with a wearing blender. Oh, it was not routine for you. Is that what you're saying? We'll have a talk about routine. I'll be talking about routine a lot because we're looking here at mixing cement. This is actually in a lab in Qatar in the Middle East. I already see something wrong with this. Can you see it on this slide? We're mixing in a wearing blender. We're rotating that blender. API says you need to rotate it at 4,000 RPM. I believe plus or minus 250 RPM. Here we're only rotating it at 2,500 RPM, but we're adding cement to the water. We've weighed out our additives, our cement. We've blended them together in our container. We've weighed out our water, and now we're adding, and we will add in 15 seconds, we'll add the cement at 4,000 RPM. We'll then increase the RPMs to 35 seconds. That should establish a theoretical mixing energy of 1 API mixing energy. That's based upon the old high pressure methods of mixing cement in the field. In the field today, we mix at lower mixing energies, but in the lab, we still apply 1 API mixing energy. Here's our wearing blender. Again, we check and make sure that our tachometer is operating at the right RPMs, that our motor is. Even the blade in there, the impeller, we will weigh it, and when it loses 10% of its weight, it needs to be replaced. And so we're going to mix up cement. I'm going to show you a couple cements. Tell me what you think about the first one. We've just added, within 15 seconds, we've added our cement. I'm not sure if you can hear the volume on this, but take a look at this nice, beautiful slurry. That's at 4,000 RPM. We're now up to 12,000. Somewhere along the way in my career, we established a mixability chart from 0 to 5. 5 was very good mixability, 0 not mixable at all, horrific mixability. And when I grew up in the oil field, we just said it was mixable, it was difficult to mix, and it was impossible to mix. So somewhere along the way, I don't know who established the 0 to 5. I do not believe that's API. But if you were grading this 0 to 5, what would you give that slurry? And the question that Vahid asked is does density have an effect in this test? Yes and no. Someone looked at this slurry before and said that's a lightweight slurry. It's not. This is a standard weight dispersed slurry. So you can disperse heavyweight slurries, but yeah, generally speaking, density, heavyweight slurries are much more difficult to mix, generally speaking. A mixability, would you give this 0 to 5? What would you give this? I still think it's kind of funny when I'm videotaping a webinar. I don't know. If I'm not videotaping, I'd like to sit back and we'll have a nice quiet conversation. But when I'm videoing, I'm thinking, anyway, those again watching my video saying, why is he talking to himself about videos? But I am waiting for someone to tell me 0 to 5, what was that mixability? Or take a guess. And while you're doing that, let me show you another one. This will look at the full mixability range, and you can tell me the mixability on this one. In the first 15 seconds or so, we're going to add the cement, then we're going to, for 35 seconds, put high energy into it. Here we go. Come on, let's add that cement. We have 15 seconds. Now, should have added it quicker, in my opinion, but now we're going to dump it at the end. Oh, here we go. And we got to tap the top, cover it up. Let's hit it. Take a look. What do you think the mixability is for this slurry? For 35 seconds, we mix it. "35 seconds goes a long time sometimes." And you know, we didn't do it here. I think I would have. API doesn't necessarily suggest it, but sometimes you'll get cement on the sides and we use a spatula to feed it in while we're mixing. And if you can hear me, what was the mixability 0 to 5 of that last slurry? Because in the old days, we would say the first slurry is mixable and it looked good, and we would say the second slurry is mixable. But we're going to grade these now, and the first one would have been graded a 5, and the second one I think was graded a 3 or a 4. And I can only imagine if we were grading that in the lab, I would want a slurry that mixed better. But we were able to mix this slurry on location, no problem. I'll continue on. I got no gradings from you on this mixability. And so I always want to check to make sure you're still there. Are you still there? Katrina comes in with a 3, right? We may be getting a delay on your answers. Okay, never mind, Octavio's there. We're good. So let's go to our first test. We've mixed the slurry. We put that 1 API mixing energy in. Our first of the 6 tests, and we'll move pretty quickly here, is density. How is density determined in the cementing lab? Most of the time, if you've been in the lab, the density will be determined how? And again, I've visited probably 200 labs around the world. API suggests that we use a pressurized mud balance, but they allow for a non-pressurized mud balance. Here's a lab up in the upper right. That's the Schlumberger lab in Abu Dhabi, where I took that picture, as we test a hollow sphere slurry with the pressurized mud balance, which we do for the hollow spheres quite often. And someone can correct me here, but I've been to almost 200 labs and rarely do I see us using a mud balance to confirm density. If I go back to the first question, I would suggest that we mainly determine density by mass balance by calculating based upon specific gravity and absolute volume factors and percentages of additives. That we calculate density, we do not measure it in the lab most of the time. But sometimes we do, sometimes, but most of the time, I don't think that's how we do determine density. API would recommend that though. We'll move to thickening time. We have our density confirmed. Thickening time, one of the most critical tests to make sure that we can safely place the cement. What is thickening time? How does API define thickening time? What is thickening time according to API? We'll talk about setting time. It's not quite setting time, Ahmed, but pumpability, specifically, Sasha and Fred both mentioned pumpability. API defines it as this: not necessarily the time from cement to change from liquid to solid, but specifically it is the elapsed time once you apply pressure and temperature. Sometimes we will simulate batch mixing and we will not apply temperature or pressure. The thickening time starts when the slurry sees pressure and temperature. But using this thickening time test, this machine that we'll look at, when the slurry reaches a consistency, which is like a viscosity, it's not, but it is, that is deemed sufficient to make it unpumpable, too thick to pump. And they give an example, maybe 70 Bearden units. Bearden units are dimensionless. They have no dimension. They are unique to this test in this machinery. And when the slurry can no longer, it's too thick to pump, in other words. For example, 70 Bearden units or 100 Bearden units, and that is the thickening time. We put slurry in a cup that has paddles. In the bottom of this cup is a rubber diaphragm. It separates the cement slurry from the mineral oil that we're heating up and pressurizing to run the test. But the diaphragm still can apply the pressure to the cement slurry. And then we turn the cup with the paddle stationary. On the other end of this, we have a stem that will place a potentiometer. And as the cup spins around the paddle, it will start to pull the paddle. The paddle will pull the potentiometer, and then we'll read that change as Bearden units. I don't know if you can hear this, but let's fill up our slurry. We obviously have to make noise while we do this. Again, quite routine. We're beating the air out of the blend, and then we're going to fill it up the rest of the way and put the cap on top. Then we'll turn it upside down. We'll place it in the machine and put the potentiometer on top of it. We'll put it in the HPHT consistometer here. We put it into this cell, which is filled with mineral oil. We'll heat the mineral oil, and we'll also have a thermocouple that runs down into the center of our test equipment that will measure slurry temperature as well. And then we're going to monitor our thickening time. We'll see the variable blue line there. That's our consistency. When it reaches a certain level, it could be 40 B sub C, 40 Bearden units, 70 Bearden units, 100 Bearden units. We call that the thickening time. When this right down here now, it's at 20. When it heads up and reaches 70 Bearden units, about 90% of the world uses 70 Bearden units as the cutoff for thickening time. For lightweight cements, we may use 40. When we're testing specifications, API for cement, it may be 100. The thickening time, again, is the time for the cement slurry while being stirred or agitated to thicken to an unpumpable gelled consistency of 70 Bearden units. Most of the world, 70. So if we start the test here, applying pressure temperature, we start to gel up, but it doesn't reach 70. Here's 20, 40, 60, 70. 80, here's 70 right here. That is the elapsed time. Let me go back. That's the elapsed time. That would be the thickening time. The transition time, we'll talk about that a little bit with gel strength. I don't know if we do this anymore, but we used to use, Schlumberger initiated it, and that was using the consistometer, the HPHT, to determine transition time. We call it a dynamic transition time, and it's the time where we go from 40 Bearden units to 100 Bearden units on the chart. It will actually correlate to static gel strength time in many slurries. Generally, we think of transition time as in the static state. We stir the cement, we then shut down, and we do this with a max analyzer, and we try to pull the paddle back through the cement, and we measure the stress. And as we gain gel strength, as we go from 100 to 500, we call that the transition time. In a bit, we'll talk about critical gel strength and critical gel strength periods, which are very similar to the transition time, and we'll talk about that. We also have something called right angle set. And right angle set is when at the very end, we don't have right angle set here, so I drew in the blue of what right angle set would look like. Rapid thickening rate right at the end. And that's really what we look for on a thickening time test. We don't want it to gel up like this particular test has done. We also have something called point of departure. Have you heard that? I've run into that most recently. Point of departure. Have you seen point of departure, POD? I'm working with some wells right now. They use point of departure as the thickening time. Mainly, I guess it's used for lightweights. 40 Bearden units sometimes is used, but some are using the point of departure. Again, I think promoted mainly by Schlumberger. Do you use point of departure? Very simply, as I understand it, very simply, and it's more of a new concept, but as we get a uniform, consistent reading here of our Bearden units, when it departs from that, and we see initial gelation, we call that point of departure. And if you use it for thickening time, can you imagine? Our thickening time here is only a short amount, so we have to then start adding retarder or doing something. And I've seen many over-retarded slurries because we're using point of departure instead of using the Bearden unit value. And then finally, I just show set time. When we think of set time, that's when you can tap on the cement. It has hardened. And I don't feel safe in any situation, and we're going to talk about that in a little bit, about using gel strength to arrest or to stop gas flow. So set time is when the cement actually has 50 PSI, and if you're not too heavy, you walk on it without breaking the cement. These gel strengths, you try to walk on cement with gel strength, you're going right straight through. These are not set cements. And just as a preview, we can't depend upon gel strength to stop the flow of gas in a well. And we'll talk more about that. We need compressive strength. And so let's talk about compressive strength. We measure it in two ways. We can measure it physically by making cubes 2 by 2 by 2 of cement, putting them in the water bath or putting them in under pressure and temperature in the autoclave. We then take that cube, and you can see it in the Tenius-Olson press. We're going to apply a force to physically break this unconfined cube of cement. And the force divided by the 4-inch area is our compressive strength. Or we can do a non-destructive test. And actually in this test, you can run a cylinder. I would recommend that you run a cylinder in the UCA. And when you're through with the non-destructive test, you can actually take the cylinder, crush it, and confirm that the ultrasonic is reading correctly. But in this case, we send an ultrasonic wave through the cement, measuring the transit time, and based upon an algorithm of either lightweight, standard density, or heavyweight, we can calculate or compute a compressive strength. That's a wonderful thing to have. We have temperature and pressure. We have our compressive strength development here. This is our transit time coming down. The faster sound travels through, correlates to this compressive strength value. And it's wonderful because we can get how much strength we have, how long it takes to get 50 PSI, how long does it take to get 500 PSI, and then what the ultimate strengths are. The UCA is a great tool. We will not touch on it, but we also have the UCA that will compute gel strengths as well. In a couple weeks, we'll talk about how much strength do we need and how fast do we need it. My biggest concern, if I have all concerns, my biggest concern is lost circulation. My second biggest concern is that we over-retard our cements. For the other tests, we're going to condition the slurry, and sometimes we will condition for just 20 minutes at temperature. Sometimes we'll ramp the temperature up according to the tests we're doing. But we will condition the slurry, often just at atmospheric. Above 190F, we can put it in the HPHT, and API shows you exactly the ways to do that, to condition the slurry, then cool it down, and then do the tests on the slurry as we expose all the additives to pressure and temperature. But most of the time, we're conditioning at atmospheric pressure with this atmospheric consistometer. And we will measure, after we condition, we'll measure rheologies. It is a good thing to know whether your lab is using heated cups as a regular routine, or if they're not. Again, my experience is most all have heated cups. Most do not use heated cups. Many do, but I would say most do not. And so when you measure the temperatures as directed by API to measure the temperature of the slurries, you'll find that they have cooled down. If you've solubilized polymer and you start cooling it down, it gets more viscous than what it would be at temperature. So make sure you're using a heated cup. And we have a sleeve here that's rotating. On the inside is a solid steel bob. And that bob is connected to, we're measuring the stress on that bob as we rotate around it, and in between the bob and the sleeve is cement, and that cement, according to how thick it is, as you shear it, it will pull, in the shear motion, it will pull on that bob and indicate a higher reading of stress. And the more you shear it, the higher the stress is. I'm doing work right now with the lab, a very big cementing company, and they do not use the API procedure for rheologies, but they note that. They note that this is non-API testing. And they will simply take the 300 reading down to the 3 reading. But the API method is to first ramp up, go low rotational speeds, 3. Here we have 3 RPMs. That's it. Up to 300 we have, and we ramp up the speed, and then we ramp back down, and we take the average of those readings. Before, as we start, we allow everything to stabilize for 10 seconds. We let 10 seconds pass before we take each reading. Some rheometers do this automatically for you, the API schedule. Of course, many do not. So we take that average reading, and we can calculate from this a viscosity and a yield point. This is a very rough method of doing it. The mud guys will use the 600 and the 300 reading. They will subtract the 300 from the 600 to get the plastic viscosity. And they'll use the 600 reading to determine yield point. Cementing does not use the 600 reading. It was thrown out in the late 80s. It felt that much shear was scattering solids and was not trustworthy. But we can do a rough estimate. If we use the readings here, we can calculate the PV and the YP. Again, the plastic viscosity calculates 95. We subtract that from the 300 reading, get a pretty high yield point, pretty thick slurry here. But you can do a rough calculation, PVYP, but most labs will have the formulas that either use the Herschel-Buckley or the modified Herschel-Buckley or a Bingham plastic. If you want to read about this, the API Spec 10 is the place to go. There's more information on rheological modeling than anything else in the specifications. But we're mapping shear rate versus shear stress at each shear rate reading as we rotate at different speeds in reciprocal seconds. And we have the slope of the line is the plastic viscosity, the intercept is the yield point. And the yield point is with no rate, or what does it take to get the cement to move at the lowest shear rate? When will it move is the yield point. We also measure gel strengths. When we're through with the rheologies, we shut down for 10 seconds. We turn on at 3 RPMs and we find where the deflection is, and that's our 10-second gel. We do the same thing when we're static for 10 minutes. Now we're also going to be measuring gel strength through a max analyzer as we slowly pull back through a static cement, or we can do it through the ultrasonics as well. Fluid loss control. This is a big one for me because we spend a lot of money buying fluid loss additives. I think it's the #1 seller. And you know, years ago, we didn't have fluid loss additives. Some people still don't use them. I'm asked quite often, do you need fluid loss additive? The answer is not always. We don't put too many fluid loss additives in surface casings, for example. Had a question the other day about putting fluid loss additive when we're in tight restrictions, pumping through bits, pumping through ports, pumping through mud motors, if you have to, that sort of thing. And as long as cement particles are moving, you're not going to lose fluid. We have problems with cement building up and plating out, but you don't need fluid loss additive just because you have pressure restrictions. You need fluid loss additives when those particles stop moving, and then we try to press the water out of them. So what we'll do, although we have various types of fluid loss cells, high pressure cells that have a back pressure valve so we can perform them at high temperatures. We have stirring fluid loss cells where you can stir the cement and then invert it, turn it upside down to prevent settling from being an issue. But the basic test is about a 300 cc cell that we fill with cement. On the bottom that where we're pressuring out is a screen. Actually, we have the screen on top as well, but is a 325 mesh screen. It's got pore openings, I think around 45 microns, but it is a very highly permeable screen that we try to push the cement through. The cement cannot go through and the water presses out of it as we apply 1,000 PSI of nitrogen pressure. And so here we're doing that. We're watching the filtrate come out. It's an exciting test. It's an exciting test if you're trying to hit a target and it's getting close. We do the test for 30 minutes. Oh, someone's beating on the can again there. Very noisy lab there. And we're going to look at that for 30 minutes. And if you're getting close to your limits of what you want, you watch it very closely. But we watch that fluid loss drip for 30 minutes. And then we double the volume to record our API value. And I guess you don't have to double the volume. It's just the square root functions of that screen that will do that. And we will calculate it if all of the water comes out before 30 minutes and we blow nitrogen through. If it, quote, blows out, then we'll extrapolate and it will be a higher reading of fluid loss value. We'll talk a lot in a couple of weeks about how much fluid loss do you need, but we test it very simply. I would ask this question: why do we use a 325 mesh screen? When I was in research, I used to have cores that I used, cores of the actual formation, and we didn't lose that much fluid out of the cements going through 2,000 millidarcy or 100 millidarcy cores. We tested unconsolidated sands that would have 3,000 millidarcy, and it was hard to get water to come out of them. But we can get a lot of water to come through screens. It's a 325 mesh screen. For ultrafine cements, we use a 600 mesh screen because the cement will actually go through the screen of a normal. Things you have to watch out for on fluid loss. There are certain additives. If you put dispersants and you get a little settling of cement on the screen, it can block the screen and you get a better result. There's a product called PVA, polyvinyl acetate, polyvinyl alcohol, but PVA that blocks the screen. And if you use it once, it can damage the screen to where you've blocked it. And if you can get a lot of fluid loss in the next test with that screen, you get hardly any fluid loss. So you have to be aware that some things can go on to change the values of your fluid loss. That's just a reporting sheet. Just to speak a bit about gas flow, every well, and we have gas flow analyzers or flow testers all around the world that's used in certain labs. We obviously don't run them on a daily basis. And I won't get into that so much as we test, quote, gas tight slurries, but much of it is dependent upon fluid loss and gel strength. Every well that we cement, every well will go under balance. And when a well goes under balance, it's going to flow. More pressure in the formation at that point than in the annular space. After we cement, I hope we're overbalanced and the well is under control. But every well, eventually, the cement will gel. You will have loss of fluid and you will go underbalanced. We just want that to occur before too much gas comes in. And fluid loss or volume loss and gel strength are very important. And that's a key reason of why we test the transition times in gel strength, that time from 100 to 500, and why we test and why we need fluid loss. The overbalanced pressure is lost due to the combined effects of static gel strength and fluid loss. That's the main reason we want to test for fluid loss. I'm never, except in air drilled holes, I'm never concerned about dehydrating the cement. If I were concerned about it, as soon as I dehydrated the first part of my cement, I build filter cake. It's not that important. As a matter of fact, when it comes to dehydrating cement, almost all the time when we get a flash set or we're worried about dehydrating, it's due to formation coming in or solids packing off. It's not due to the lack of fluid loss, in my opinion. But I am interested in having low fluid loss, especially that I keep the overbalanced pressure in the well after I have placed the cement. So we have something called critical static gel strength, or we talk about how gelation stops the flow of cement. So I just want to stop on that briefly. As I prepared for this, some people asked me, and I promised I would touch on this. Here's what API says. In API standard 65.2, this is based upon research. Matter of fact, some old bosses of mine did this research back in the 80s. So this is 40-plus-year-old research, and API writes this. Experimental data has shown that gas cannot freely percolate. Important words. Cannot freely percolate due to buoyancy, the percolation of gas. Gas cannot freely percolate through cement that has a static gel strength ranging from 250 to 500 pounds per 100 square feet. The industry has conservatively adopted the upper end of the range as the accepted limit. In other words, at 500 pounds per 100 square feet, the industry has accepted that bubbles will not freely percolate. We can mistake this to say at 500, gas can't flow through cement at 500 pounds. It doesn't say that. It says cannot freely percolate. Those tests were done by having an injection nozzle in a tub of cement and watching bubbles percolate. That nozzle was of a certain size, creating a certain bubble size. The differential pressure was only 1 psi. So we were creating bubbles, putting bubbles into the cement to see if they would float up. As you see bubbles float up in a Coca-Cola or air bubbles in some sort of fluid, you watch them work their way up. This is not directly related to what pressure builds up and allows channel flow. It doesn't talk about what other fluids come in with the gas, like mud or formation fluid. It doesn't talk about the variations of gel strength development in the wellbore. So there are a lot of things, including if I nipple down BOPs and start moving my casing and break gel strengths. So we got to be very careful thinking that, hey, if I can get that gel strength, I'm okay. At the same time, for a gas tight slurry, we want a fast gelling, fast setting cement. I'm going to skip through that due to time, and let's go to the free water test. So critical gel strength, let me just go back to it, is how much gel strength do I, when I get to a certain gel strength, do I lose my hydrostatic? We say the transition time starts at 100, but it could start sooner or later if I can calculate when that gel strength has caused me to lose my overbalance. And then my transition time is from that gel strength up to 500. I hope that's clear. Final test is the free water test of the 6 tests that we do. We will condition the cement. We'll pour it into a cylinder. 250 milliliter is the usual that we use. I think you can go down as low as 150 allowable. And I suggest we place it in a water bath. API allows for an ambient free water. I would say 90% of free water tests run around the world are done at ambient conditions. That doesn't help me. I want to know what is going on downhole. And it's always, almost always, more severe at temperature than it is at ambient conditions. Again, especially if you stir in polymer, heat it up, and then you cool it down, it's going to reconstitute itself, gel up. You're not going to have any free water at ambient, but you will have a lot of free water, perhaps, downhole. And we place it on a foam pad, trying to stop vibrations from separating out the water. So here we're in the vertical. We put a cover on top. It can be a cork or a cellophane or aluminum, just on top to prevent evaporation of free water. And we watch it for 2 hours. How much floats out? Is there a streaking of solids? We observe that sort of thing in the free water test. We can run it at vertical, or more critically, we can run it. Here it's placed in an oven. So we're running it in an oven at temperature, and we're running it at a 45-degree angle, which is the most critical angle where you get the most severe results. And then you see some water floating out, and there was always a debate, is it free, clear water, or is it colored water, or is it that sort of thing? API will tell you it can be clear or colored water. It's that separation right there is the free water amount. I don't know if you ever see this, but I see a lot of things I don't like to see, which is on the report, a trace of free water. I don't know what a trace of free water is. We should be measuring this to 0.2, I think, or I think API says about 0.2 milliliters, but we'll say a trace. I want to know if there's a visible, measurable amount of fluid on top. What does that matter? We'll talk about it in design, but I see many labs putting some amount of gelling agent in just to take care of that minor free water. A little added cost, more added viscosity, which I don't always like. But here we're looking at free water, that little bit right there. And the free water test, again, I recommend that it's done at bottom hole, at least bottom hole circulating temperatures. We can do additional tests related to free water, namely settling tests. And we'll look at about 5 or 6 additional tests over the next 30 minutes. The BP settling test, we're going to, and you can get a BP settling tube. This thing is about 8 inches tall, 8.5 tall, a 2-inch diameter, and we will fill this with cement. It unfolds, this mode does, where you can easily open it. And we're going to cure the cement for 24 hours in an autoclave or in the HPHT consistometer. And so when we're finished, we have a cylinder of cement that's about 8+ inches tall. We're going to cut off the top and the bottom 3/4 of an inch. And we're going to take what remains and we're going to break it into pieces. How many pieces does API say that you break it into? I got to double check that. I think they say you can break it just into 2, but you break it into equal sections. We normally will break it into 6 pieces, maybe 4 in some areas, but again, it's not fully specified that you have to have exactly this many pieces in API. So we separate it in this case into 4 pieces. We cut them, physically cut that cement up into 4 fairly equal, and we're going to measure the density of each of these pieces. Our standard has always been that and I know it changes as you go various places, from top to bottom, you should not vary 10% in density. We will measure the density using the Archimedes principle or method. Very simple. All you do is take that piece of cement and you weigh it in the air, just on a scale, you weigh it. The example shown here, it weighs 500 grams, let's say. You then suspend it by a thread and you submerge it in water and you tare the weight where it's, and you see by adding the water, the cement into the water, what the weight is. And you take the difference of that weight, and that's the amount of water that you've displaced. And so that's the volume in grams that you have displaced, because water, 1 cc is 1 gram. So you now know the volume of that piece of concrete, of cement, and you know the weight in air. So you just simply divide the weight in air divided by the volume of water displaced, and it's 500 over 80 in this case, and you get a density of the cement. So we measure the density of each piece in the BP settling test. We have another settling test. I don't know if you've done this. Has anyone done a dynamic settling test? Has anyone performed a dynamic settling test? This is done in the HPHT consistometer. Was very popular. I don't know how popular it is now, but it was very popular as we began unconventional wells, long horizontals. One of the problems we would have, when we pumped the cement, when we went back in to frack the wells or to clean them out, we had left a lot of cement on the bottom of the well. We're also concerned about settling outside the well, but we were settling a lot of cement inside the horizontal. So here we use the standard, we mix the slurry up, we use the standard way that we do a thickening time, but after the thickening time is done, we slow it down. The paddles are removed in this test, but we're still running inside the chamber, and it's a flat plate on bottom. And now instead of 150 RPMs, we're turning this at 25 RPMs, and we're going to observe, pull it out at the end of the test, and we're going to observe how long do we stir that? I don't know why it escapes my mind. I want to say that we stir it for 30 minutes at a low rate. I actually have the feature here. Let me check that out. We stir it for, we stir it for, once the desired temperature and pressure conditions are reached, continue stirring at 150 RPM for 10 minutes to be sure the slurry. Reduce the stirring speed to 25 RPMs to maintain the final temperature and pressure conditions. Observe for at least 30 minutes is what we'll do. And then we'll cool the machine down and we'll pull it out. And what we'll get as we test this at a low speed for 30 minutes, if it is going to settle, we're going to get some thin slurry we pour out, then some viscous slurry, and then we're going to start getting some cones. And we're mainly interested in this cone area. We'll wash it with some water and see how much has settled out. It looks something like this at the end of the test. This is what has settled out. And we used to say we will pass if we have less than a ½ inch, as we have here, of settlement as at the top of that cone of settling. And so this would pass the dynamic settling test just barely. We started opting off of the dynamic settling because we would find this, that we could pass the dynamic settling, you see it there, but if you look at the free water test, the free waters were falling apart at temperature, or at least at elevated temperatures. And we just found that at temperature, the BP settling test was more effective, but if we wanted a quick test, just the free water test at 190 for our slurries were more severe than the dynamic settling test. That's how that test is run. Additional tests that we run, the shear bond test. Do you ever test shear bond? I used to carry a mold with me wherever I went so that we could run shear bond tests. Most of the local labs do not have shear bond molds. And I don't have the schematic to the molds, but shear bond to me is very important. How tightly do we bond to the casing? I'll talk more about that when we talk about acid solubility tests, which are really important in today's world of CO2 storage and sequestering. On the left is the bond log, not well bonded, a lot of straight lines. We see the collars ringing. This is a low shear bond cement. Here's our high shear bond cement, much better. The attenuation of the sound. The high shear bond, we can measure the shear bond of our cement. We do it through molds. I don't have the schematic here, but it is about a 4-inch size pipe, and we cement a 2-inch pipe about inside of it. So we actually cement in this mold. We have a plate on bottom and top, and we cure the mold pipe in pipe. We remove the plates and we put this on a stand where we can push this pipe down through, and we put it on the Tenius-Olson compressive strength machine, and we push until we pop that pipe out of the mold, until we break the bond between the cement and the inner pipe. Shear bond is the force divided by the area of the cemented model, the height multiplied times the diameter times pi to get the area. And we measure shear bond. I don't know if you run shear bonds, but the molds are available. We're there to bond, and we'll measure expansion and how it helps with the bond. But when we talk about trying to protect our casings or try to get zonal isolation, it's not just good cement, it's a good bond with the cement. So I think shear bond's very important to run and know for your cements. We do expansion testing. We use various molds. When I first did expansion testing, we would use long these longitudinal modes, and we'd measure how they grew. Mostly we use a couple different types of modes now. We can put them in a cube mode with springs and measure the expansion. Most often you'll see the mode on the right, which is a radial mode. It's a ring mode where we get a ring of cement and we fill it with cement in that hole, and then we cover it with the grease, and we cure them in the water bath or in the autoclave. And you can see the expansion here as this is growing out of the cube. I remember some of the first ones I did, we didn't have the spring loading here, and we would actually bend the modes with expansion. But we put different products in. We can put a gypsum in with the Class A cement. We can put magnesium oxides in regular cements, and you get a post-set growth of the cement structure. And then we just simply watch it day by day. We take it out and we measure it of how much we're expanding. Most often we can do it also with the radial mode, seeing how those beads grow apart. And our target expansion is somewhere between 0.3 to 1.2%. You want good expansion. You don't want to over expand the cement, however. Compatibility testing is another test that we conduct to see if not only the spacer and the muds are compatible, but looking at cement, is the cement and spacer compatible? We'll even test the cement a bit with the mud. Normally we will assume the mud is not compatible with the cement. We do it at various percentages. We simply mix up spacer, mix up cement. We have our mud, and we'll add in different percentages. It ranges from 100% to 95-5, 75-25, and 50-50 of each material. And we put these in, mix them together, and use a spatula and simply stir them together. And then we'll measure the rheologies. And yes, Julian, we'll be sending a recording out. Thanks for joining, appreciate it. You even see at the bottom here, again, as recommended by API, to mix mud, cement, and spacer all together. When we do compatibility testing, I don't think this is API, but many use an R index value. Again, I think that comes from Schlumberger's labs, where, just as an example, we compare the 100 RPM readings of the mixtures and of the thickest of the two products that we're mixing together. In this case, I'm assuming the cement is the thick, and we want all of the rheologies to fall between the thickest and the thin. We want it to be a nice linear or in between. We don't want it to get too thick or thicker than either of our base products. Therefore, we expect the R value to be less than 0, but consider it compatible even if it is between 0 and 40. Above 40, we consider it incompatible, severe incompatibility greater than 70. It's just a comparison of the 100 RPM readings. Kind of a very pertinent kind of test that we often do in the labs is to check and see if our cement is acid soluble. This is very important now as we move into CO2 storage. CO2 injection always have been important, but now that we're looking at storage wells, again, I was just up in Illinois where they were teaching me about all of the projects going on in that area to sequester carbon and to pump CO2 into wells. We want a cement where we'll not corrode and maintain isolation as we pump what can be corrosive fluids into the wellbore. We have products now that we're marketing based upon acid solubility. And so it's important to know how those tests can be done, how reliable, how how we achieve that. We'll talk much more about this in 2 weeks when we talk about designing acid insoluble cements or acid resistant cements. Let me give you a few examples and understand that corrosion requires not just solubility. You're going to have certain companies sell you a cement that is acid resistant based upon solubility numbers. And that's one part. It's also important to eliminate exposure to that acid. So you need good bonding as well. And then also there is a transport as you try to corrode cements. The byproduct is an insoluble salt that you need to transport away to continue to corrode the cement. So when you have solubility, exposure, and transport, you can have a decay or a corrosion of the cement. Very important, here's an ultrasonic log showing corrosion, bad corrosion that has eaten through the casing. And if you look at the amplitude curve, which I call the casing inner surface, you can see those holes in the casing. You can look at the casing radius as well, and you see the red where it has diminished. Look at the casing thickness. And this is casing thickness. You can see a channel occurring. And look at the cement. You can see a channel occurring. Interestingly, on the wide side, this galaxy pattern showing us the narrow side of the annulus. Now tell me this, where is the channel occurring? I've got two stories here. Is it occurring in the casing or is it occurring in the cement? The way we are set up to measure ultrasonically, you get the exact replica in the cement as you do in the casing. So if you look at this, answer that for me. Where is the corrosion occurring, in the cement or in the casing? It appears the casing, doesn't it? Now, I don't know, we may have corroded some of the cement, but this goes to just confirm even more. If the cement doesn't corrode, but I don't have good bonding and I corrode the casing, I still have a channel. The bonding is critically important. It's interesting as you look at steel corrosion versus cement corrosion, that really can be about the same, only maybe steel occurs slower but more consistently over time. I'm going to show you 3 acids and how we've tested them. Much of my testing has been for this. As I've worked for various companies, we've tested acid solubility many times in the lab. Here we're testing in a pressure cooker, constantly feeding in the CO2 and creating the carbonic acid. We test specimens, and what we achieve is more of a dissolution of the calcium out of the cement, out of the Portland cement. It more brings it out of solution so that you get a pitting. I don't know if you can see more of a pitting of the cement in certain cases more than others that are more acid resistant. But we don't put these in carbonic acid and they just fall apart. There is a dissolution and a selective pitting. And the way we design around it is very interesting to avoid the CO2 causing corrosion. In hydrochloric acid, when we put the cement in, once again, an insoluble salt surrounds that as it tries to invade the cement. So we test it in various ways. We stir it to keep transport occurring. We even take them out and scrub it with a brush to get rid of the insoluble salts and put it back in. We can get very aggressive for how we allow the acid to attack it. Because if you put a cube in and just let it soak, you create an insoluble salt and you do not get much corrosion at all. So I can report no corrosion. In fact, once I start transporting and removing that insoluble salt, it can be quite corrosive. Here's an examples of doing some hydrochloric acid tests. The really bad one here, slurry 2, actually we removed the Portland cement, replaced it with pozzolans, but the pozzolans were very acid soluble and it just fell apart. So the only way to know if your cement is acid soluble, in my opinion, is to test it and to see, and we stopped using that particular pause for our cement. Sulfuric acid is another. We did a project on geothermal wells near a volcano in North Sumatra, where we had fumaroles like this of sulfuric acid, bubbling sulfuric acid in the rock, and we lowered hundreds of cylinders of cement and measured over weeks and months the corrosive nature of the cements. We were doing this to test an anti-corrosion cement, a calcium aluminate cement, and that is shown on the left, our Portland cement on the right. And if I were to suggest this is occurring with huge transport and exposure. Not something we get behind the casing. This is the most severe case. This is the attack, and there was some CO2, some carbonic acids in this as well, but this is an attack on Portland cement on the right, which I would be concerned about if I felt I had exposure. So we need to do that. Having said that, that cement on the left that had almost no corrosion from the sulfuric acid also didn't like to bond to casing. Pretty interesting. You need both anti-corrosion and strong bonding, again, to prevent fluids from coming up and corroding the casing. Generally speaking, we have special cements down as shown below that go from 0 to 1%, like the calcium aluminate cements. Schlumberger has a very popular product that they promote called Evercrete. I don't know, I know it lacks a lot of Portland cement. I don't know the exact formulation of that, but I would imagine, because I've tested a lot of Schlumberger cements, that it has very low permeabilities, that it has good low fluid loss. We find that the more, the less permeability that we have, the tighter that is, the acid cannot contact it, and the acid solubility is very low. Generally speaking, Portland cement will be as high as 40%. According to what the pause mix is, it will lower it, but we have some pause mixes that will be attacked by the acid. Low fluid loss slurries, which would include latex slurries. Now we add pause mix with low fluid loss or latex slurries, and we get down in that very low range. We do a lot of other testing. I've only touched on just a few, really. We do a wettability testing. We do special testing for foams, foam stability. We go on, we could list tens of tests. I wish we had all day. At our course that we provide, we go into a lot more of the testing and we go do hands-on. But I would like to summarize by saying this. The cement lab is the heart of the cementing operation. If we can connect that to the field and to results, that would be a wonderful thing. It is a set of learned routines that are different for every lab in the world. So learn and know how your lab performs those tests. And make sure that they're solid, that the routines that were put in place are good routines that tell you what you need to know, that tell you that your free water and your stability of your slurry is good down hole, not just at surface. Understand those learned routines. API provides a very good guide to that routine. I believe lab testing should mimic actual conditions as much as possible. The more we can link reality to the lab, the better. And in talking to our lab personnel, and even outside as you direct the lab, if you're with an oil company, be a leader in that cementing lab operation, and you have to be careful. When I go into a lab, I'm not there to say, hey, here's how I do tests, do them my way. I just want to learn how you do your tests. I don't want to upset your whole operation and have you doing special tests for every oil company there is, but I want to know how you're doing them to know what I need to understand about how we design our slurries. And if we can do some small changes that make it more real, then we'll do that. But understand the practical application of the lab test results. When I get a fluid loss value, what does that mean to me in the field? How would that apply? Because I'm no longer across the 325 mesh screen or my gel strengths. Cement labs, my final point, should be continuously used to continuously improve the cementing operation. A concern that I have is now that we're making things more efficient and cost effective, and the service companies are forced to do that, we try to get more uniform slurries, less inventory of additives, more uniform design. And even if they're not meeting the test, it's the system we got and it's the system we're using. And sometimes it's hard to change those designs to get better results. I don't continue improving because I've landed on something that's efficient and easy and cost effective for me to use. But can I test that? Can I make changes through the lab to make it more cost effective, a better slurry? Well, I want to thank you for attending the webinar. We'll have time now for some questions and answers and discussions, but appreciate you attending the webinar. And we will see you at the next one in a couple weeks on slurry design.